All right, welcome to the new and improved and hopefully shorter version of CSE 215 videos. So I'm going to try to keep these videos to really talking about the main points, and then we'll explore the details of these points during homework exercises on the board. So first thing I want to talk about is prime numbers. And you're probably familiar with the notion of a prime. A prime is an integer that's only divisible in the most trivial ways, namely by 1 and itself, or -1 and negative itself. But it doesn't have any sort of genuine factor. So for example, 7 is not divisible by 2, 3, 4, 5, or 6, right? So that's prime. But 9 is not prime because it's divisible by 3, so we call it composite. And the reason is that there's a number 3 which divides 9. So primes have been studied for thousands of years, and they turn out to be really useful today because, for one thing, they tie into cryptography, and the public key crypto systems that we're going to talk about at the end of this unit all boil down to being able to work with primes and deal with primes in interesting ways. So first question is, how do we tell if a number is prime? Right, so we're going to work on this on the board, but basically the easiest way to test if something is prime is to see if it has a factor. Okay, but how do you test to see if a number has a factor? You can divide it by every possible integer, right, but there's an infinite number of integers. So we'll work on the board and see ways to refine that. But first order way to tell if something's prime, just start looking for factors. All right, now there's this important fact about prime numbers. This is called the fundamental theorem of arithmetic. And it basically says that prime numbers make up other numbers in a unique way. For example, the number 9 is equal to 3 squared. And there's no other set of primes, right? 3 is a prime. There's no other set of primes we can multiply to give us 9 other than 3 and 3. Let's pick a different example, 36. We know that's 6 times 6, but 6 is not prime. This is actually 3 times 2 times 3 times 2. That's how we write 36 as a product of primes. It's basically 2 squared times 3 squared. And this fundamental theorem of arithmetic tells us that this is the unique way to write 36. Other than the obvious rearrangement, we could write 3 squared times 2 squared, or we could write 2 times 3 squared times 2, but it's the same powers of primes. And this is what the fundamental theorem claims is unique. And it's a really powerful theorem, and it's not true under other number systems, but under our system of integers, this is true. Numbers can always be written uniquely as a product of primes. And for a prime number itself, this is just 7 equals 7 to the first, for example. That's the unique representation. All right, so that's the fundamental theorem, and we'll play around with that on the board also. Next concept is something called a Mersenne prime. And a Mersenne prime is a prime of the form 2 to the n minus 1, where n is an integer. And we hear about Mersenne primes because these are really the form of the largest prime numbers that we've discovered up to this point. Why? Because if there's a prime in this form, we know a lot of things about it. For example, there's a famous test called the Lucas-Lehmer test that will let us test numbers in this form to see if they're prime. And it's a whole lot simpler than dividing by every possible integer to see if this thing has any factors. So these are the forms of the largest primes that we know of, and we'll explore that on the board doing some work. Next concept is the number of primes. So how many primes exist? And the answer is infinite, right? Infinity is not a number. It's a concept which says there is no integer that is bigger than what we're saying is infinite, right? So there's always another prime, and we'll prove that in class. And that proof has been known for thousands of years also, that there is no largest prime. Whatever number you pick, there's always a prime bigger than that number. That's the sense in which the answer to this question is infinite. All right, interesting fact, distribution of prime numbers, or density of prime numbers. So let P of x equal the number of primes less than or equal to x. So how many primes are there up to any given number x? And here's an interesting fact. As x goes to infinity, P of x gets closer and closer to the natural log of x. So that should be a little weird to you. That's actually a very weird fact. The number of primes is related to the logarithm base e of the number x. And it's not exact, obviously, but as x gets bigger and bigger, this approximation gets closer and closer. And this takes us into things like the Riemann hypothesis and the zeta function and all kinds of really crazy concepts related to primes and integers. All right, so last thing I want to talk about are open problems. And there are a lot of open problems related to prime numbers. So one of them is the twin prime problem. So what's a twin prime? It's a pair of primes separated by 2, for example, 3 and 5, 11 and 13, 17 and 19, 29 and 31. And we find, no matter how large a number we look at, we find pairs of these twin primes, no matter how far we go, no matter how large our numbers are, we always find another pair of twin primes. But nobody has proven that there's an infinite number of twin primes. It's possible that there's some number n, and above n, all primes are separated by more than 2. It's possible, it's never been proven, but we've never found a case of an n where we couldn't find twin primes larger than n. So that's an open question. Another open question, which you'll have a programming assignment about, is called Goldbach's conjecture. And this conjecture is very easy to state. It basically says if n is even and n is bigger than or equal to 4, there exist primes p1 and p2 such that n equals p1 plus p2. In other words, every even number bigger than 2 can be written as a sum of 2 primes. So pick your favorite even number. Let's say we took the number 12. That can be written as 5 plus 7. 14 can be written as 7 plus 7, and so on. So we'll explore that in some homework questions also. All right, so next video we're going to talk about greatest common factors.